Okay, directional derivatives and gradient vectors. So, in general, yeah, first we just find gradient vectors of this form, and if you have a third one, of course, you add the z variable df dz. Okay. But yeah, for the x and y at point p0, x0, y0 is this. And the derivatives are at the points x0, y0, of course, plugged in. So y minus x 2, 1 basically is a function, and so p0 is 2, 1. But it doesn't matter for this one because you see you take the two partial derivatives, yeah, and like you get negative I plus j because it's negative 1 and 1, and then you just plug in that this formula, so negative 1i plus j, negative I plus j. Yeah, maybe make a note there. And when you sketch it out, the level curve is y minus x equals to a constant value, so it's just 1 minus 2. So y minus x equals negative 1, and y equals negative 1 plus x basically is how you can rewrite that to make it easy to graph. When sketching, you sometimes want to make it easier to graph. There is the equation, and the gradient comes off at that point. Same thing for this one, as you can look at it. Just I don't think it's the biggest concern. Yeah, I ignore that. It should be at the exact point. That gradient is at the point. You have to remember that this time especially. It's at the point because it's a little bit more complicated and depends on x and y. The partial derivatives change value at different values of x and y. In level curve, basically I just had this function squared equals the square of when it's valued. So you get 2x plus 3y equals 4. That's the square of this at 2 times, Eventually you just solve for y. And you get another line. But I think there's more to this section that matters. But you can look at these and you should understand them. And with 3 variables, we don't even do a sketch. Because obviously it's a lot harder. It's really hard. Like you can't generally sketch a 3-dimensional thing without using some kind of software. So, and as you can tell, I realize this is overcomplicated how I did it. So not overcomplicated, but like basically this one's relatively simple. It just seems like a lot. But you have a very similar derivative for each of them, just with slightly different variables. But it's like before, like this was an extra thing, and you plug it in for the point. A lot of work to do that but you're just trying to get the gradient here. These first ones I was sketching them along level curve and it. This time we're just doing the gradient, no sketch required. And that's it for pure gradients though. So the next 2 problems involve finding the derivative of the function at p0 in the direction of u. So we're doing directional derivatives. We have to make it a unit vector for this formula to work. The uf equals the gradient f times dot u. It's the dot product. And you have the function xy plus yz plus cx. p0, 1, negative 1, 2, and 3i plus 6j minus 2k is the direction. It's given as u. You could use a different letter, but let's just assume like normally this would be like v or something else, and u would be the unit vector. Which will you get? But so you solve the gradient. Then u is equal to just the vector divided by the length of the vector, or magnitude of it. And you eventually get basically the vector divided by 7, each component. And you do dot product of this, and you get eventually, through the dot product, just the value of 3. Because it's a dot product, we get a definite value, a single value, single numerical answer. This one, 3e to the x times cosine yz, 3 points, 0, 0, 0 to point. The coordinates are 0, 0, 0. And direction is 2i plus j minus 2k. I just showed taking the derivatives, the three partials that we need. And it's 3e to the x times cosine yz, so anytime the derivative of x is going to be, it's the same thing basically, because e to the x is e to the x, and everything else is constant. So it's, the constant times e to the x, the derivative will be just e to the x times the constant still. And these ones don't involve, 3e to the x becomes a constant in these ones, so you don't have to worry about product rule. Product rule does not apply, at least here. So in the end, it's just the derivative of cosine yz that really matters for these two, and it's really only changing slightly depending on which one it is. At least solving for 0, 0, 0 is relatively simple with exponential and the sine cosine functions. But you eventually get 3i plus, just 3i. And at this point, the unit vector, you make it a unit vector direction, so you get this, then dot product. It's obviously going to be just 3 times 2/3, but yeah, you can put the zeros in. Eventually you get 6/3 plus 0, which is just 2. 6 divided by 3 is 2. Those are directional. Okay, now we're going to go into like finding out where the greatest change occurs, where it increases and decreases the most. Because this is directional derivative. And it changes with different values, generally speaking, so it matters the rate of change and all that. It's a derivative, so rate of change does matter to some extent with these. At least when you want to care about it. So you use the fact that a unit vector has a length of 1 always. Sort of the definition of it, but it also can be checked many times you do it. But anyway, then duf equals gradient f times cosine zeta. This shows that cosine zeta equals 1 is where function f increases most rapidly. Zeta equals 0 here. And just looking at this. Yeah, these rules, this is basically the sweet. I mean, we're not going to really worry about this zero change one. It makes sense, but basically no. The point is the dot product is basically the two magnitudes, the product of magnitudes in cosine theta. And because that's magnitude of unit vector.
It's amazing I didn't have a heart attack or stroke myself during that 20 minutes in court.
But what the family found next turned their devastation and anger.
F decrease, so basically cosine theta times the magnitude of f, gradient f, is all that the directional derivative is equal to, really. So if you have theta equals 0 where cosine theta equals 1, you get the highest where function f increases most rapidly, and the opposite is true when it's negative gradient, or where theta equals pi. So cosine pi is negative 1. And that applies to the next part. We want to find the direction in which the functions increase and decrease most rapidly at p0. Then find the derivatives at the functions in these directions. F of xy equals x squared plus xy plus y squared. P0 to the point is negative 1, 1. It's just a two-dimensional one. I mean two variables. And we're going to use this to exemplify something. Gradient f in negative 1, 1 will be, so it's, you have to take the derivatives, 2x plus y and x plus 2y for two partials. Then you do, of course, the gradient at negative 1, 1. Just plug them in, x and y values to these two. You get negative I plus j, so it's a pretty simple one. So we make a unit vector out of f here. So you get negative 1 divided by square root of 2i plus 1 over square root of 2j. And that's the direction. Then derivative in this direction is found by doing duf, like before was our unit vector. And the original gradient, which through some manipulation you get to be square root of 2. Or can we just 2 over square root of 2, or square root of 2 does the same thing? But what matters most is that's the first part. Now you have to find the direction which it decreases most rapidly. But we have an alternate method we'll show in a minute, but first do the same thing but with negative. So you can just make the negative unit vector by switching the signs. So do the directional derivative in that direction. It's the original gradient and this negative direction. You get negative square root 2. So that's your direction and the derivatives in which they fall. Now, I'm using unit vectors for direction here. It may be acceptable by some instructors to not do as much as I showed, so you basically go by whatever your instructor wants. If he shows only the one method, use that method. If he shows this way, it's easier. I mean, you get the same derivative value, it's just that the direction is kept simpler. It's not unitized, basically. So f decreases most rapidly. We'll do the decrease instead of the opposite way. We'll do decrease then increase. So direction of negative del f at that point. So this is just I minus j, that's the direction. And the derivative in this direction is negative of the magnitude. So it's just negative square root 2, which is the same up here. I did this. Only difference is direction, but you get the same thing, negative square root of 2 for the derivative. And this applies similar to where f increases most rapidly. So you get square root of 2, and we got, they're going to be opposites in sign, basically, these derivatives, in the direction of most rapid decrease and most, rapidly increases. And the direction is just is gradient of f, see, very convenient, negative I plus for the increasing. And next two, you'll see this from the beginning, and it only takes less work, generally speaking. And this time we have x, y, and z, and it still takes less work overall. So f increases most rapidly at this gradient, which we find by doing the partials of this function, x divided by y minus yz. Of course, x divided by y, when it takes derivative with respect to y, it's x times 1 over y. So it's y to the negative 1 power becomes y to negative 2 power, and you get the negative 1 out. But we're not worried about derivatives and stuff, we're worried about what's new here. It could take forever, this could take hours if you go over very little detail of stuff from the past. But math is something that builds upon past lessons. So the gradient of f at the point 4, 1, 1 is given, so you plug in for those partial derivatives with your gradient formula and everything, you get direction where f increases most rapidly at p0. I minus 5j minus k. Then the magnitude of that is 3 square root of 3, so that's your derivative. Same thing here, negative of that, you just swap signs and you take the negative gradient, which is negative 3 square root of 3. That's it. Now finally we do the same thing to this one. Arguably a very simple derivative if you know what a natural log is. If you don't, you're out of luck. So basically your natural log derivative is always very important to understand. So then you get at 1, 1, 1, which is a very simple point. So you have 2i plus 2j plus 2k is what your direction is the most rapidly. It increases most rapidly in that direction, and your derivative is 2 squared is 3. Same thing here, negative of that, just negative 2, negative 2, negative 2, like the I, j, and k. And it becomes negative 2 square root of 3 magnitude. It's derivative, I mean. Finally, in 25 and 27, we sketch in a level curve type thing together with gradient f and the tangent line at the given points and write an equation for the tangent line. Just a good way to sum it up, like a shorter exercise sort of overall. Just doing a lot. So you're given, this is the level curve. X squared plus y squared equals 4. It's a circle. Radius 2. You notice by now. 2x and 2y are the simple partial derivatives. This is a constant on the side. You can technically subtract 4, but it'll be the same thing. You can write it as that. But you can just take it right away. Square root of 2 is the point we have to plug in for. So it's just 2 square root of 2i plus 2 square root of 2j. So that's your gradient. It's a tangent line. You have to do this formula basically, fx. So you take the partial derivative of x with respect to x, partial derivative with respect to y, or fy and fx, at the point given. Square root 2 square root 2 basically in this case. And x minus that x point and y minus the y initial point. That's all you do, and you eventually get y equals something out of it. Some kind of combination. Y equals negative x plus 2 square root 2. It's a linear line, so it's easy. And the tangent line is going to be a straight line. That's why you do it like that. Trying to get tangent. As you know, a tangent only hits something at one point. You have the circle, you have that, and you have the gradient coming off it. Finally, level curve here. Yeah. xy equals -4.
Fox decided to investigate.
We can redraw that as y equals
She discovered that GPS monitors can't be.
-4 divided by x, or -4 to x minus 1 value. -4 divided by x gives you the implication that it's going to increase really high in the when it gets to close to 0 from the negative axis, but it'll really be low for a while until it'll approach 0 as it goes from the 0 to the positive number. Obviously, it's undefined at the point
No geographic restrictions and
x equals 0.
no curfew programmed into it. What's the point of it?
Exactly.
Is part of it that it's
That's the level curve graphing. Now, thankfully, partial derivatives are as easy as can be. Just y and x. Y is though for I and x is with, But at 2, 2, it's at 2, -2.
commissioner of probation?
Yeah, it just kind of. So df dy is x, so that's 2 here for j. df dx is y, and that's -2.
False sense of security.
Just pay attention to that. And they'll come off of it to -2 point. And the tangent line, again, is the same process. Yeah, 2, -2 will be on this side of it. It's a hyperbolic-based function. I'm pretty sure hyperbola or something like that. It's not a normal function, basically. It's not like your perfect polynomials. It's not a standard polynomial.
People wearing GPS monitors, but we did our own search.
And that's it for this section.